Okay, thank you very much. So let me start thanking the organizers for the invitation, especially Francisco, who told me about the conference. I didn't know about the conference. It's very nice, and it's very nice to see a lot of friends that I don't see very often here. Besides, usually in January I go to Chile, so this time it was frustrating. So at least I feel a little bit like that. So I will talk about infinite dimensional symmetries that emerge in the near horizon geometries of black holes. And even though, as the title says, I will focus especially on the case of extremal black holes, where, as usually happens, some special features appear, half of the talk will be general enough. So I will talk about black hole horizons in any case, so not necessarily extremal. And you will see this because there is kappa, the surface gravity, which for extremal black holes is 0. You will see it appearing in the expressions, because as I mentioned, half of the talk at least will be about, for any black holes, extremal or non-extremal, apparent horizon, even not necessarily isolated horizon. So it will be general enough. So let me just mention that this is based on a series of papers that I wrote in collaboration with friends from Chile, Brussels in Belgium, and also then these people were traveling around because they were postdocs. So also I had to mention other institutions like Harvard, Vienna, or Paris. But so these are my collaborators: Logadoné, Hernán González, and Miguel Pino, and also Andrea Pum. So, and this is, it will be based on these papers, but also is motivated by a series of papers, kind of simultaneous, that appeared between 2015, 2017, and even more recently, notably by Hawking, Perry, Strominger, and Jacob, and other papers that I'm not mentioning here. So we can consider this as a summary, but there are also other groups working on that, and other colleagues like Ricardo Troncoso or Daniel Grumil or Sheikh Jabari. So let me start by saying what kind of symmetries I will talk about. And these symmetries are BMS symmetries. But first, let me summarize what BMS symmetry are and how they appear originally, because the context in which they appear, even though it's also gravity theory, is a kind of different. So let me then start by saying what is BMS symmetry. And BMS symmetry is is actually a very old observation coming from 1962, which is this is the symmetry, infinite dimensional actually, that generates the asymptotic symmetries of asymptotically flat spacetime. So this is the Penrose diagram of asymptotically flat spacetime. I will be, for those that are not familiarized with Penrose diagrams, I will be a little bit more precise in the next slide. But let me say the context. So these people were considering asymptotically flat spacetime and massless processes there. For instance, gravitational wave scattering, or if you want, photon scattering. Doesn't matter if it is gravity or electromagnetism or whichever massless field you are considering. You just consider scattering processes like the symmetries, incoming waves and outgoing waves, massless. So you know that these guys, these massless will go to asymptotic very far region in asymptotically flat space-time. It doesn't matter what happens in the middle. You can have some waves that come, some nonlinear effects in the middle, and then scatter back. So basically, if you consider the scattering, the matrix processes, you will be interested in the asymptotic region. Okay. So what these people, Bondi, Messner, and Sachs realized in 1962 is that the symmetries, the asymptotic symmetries of asymptotically flat spacetime is actually not Poincaré, but larger, and is infinite dimensional. Okay, and this is the BMS group. I will be precise in the next slide. And then mention this is the classic references. There are like 3 or 4 references of these people, and then these are a kind of peak. Gaston's pick of the recent papers on that I consider very interesting, because all this story of asymptotic symmetries in asymptotic flat spacetime have been recovered and reanalyzed from the modern perspective recently. So let me continue with this propedeutic analysis, preliminaries about what we have to know about BMS to understand this topic. So this is again the Penrose diagram of asymptotically flat spacetime. So we are here living here in the middle of the spacetime. okay? And also I'm very egocentric, so this is the center of the universe, and I'm located there, R equals 0, so I'm here. What is this point? This point is the spatial infinity. What does it mean? Is I freeze time and go, and then at freeze time, frozen time, I go to infinity now. This is this spatial infinity. And then this is the future infinity. What it means is where all the massive particles go eventually. You know, or if you want, you just don't move, just stay here, and then you will end up in there at time infinity. But then there is this notion of null infinity, which is this null direction. Okay, this is a Penrose diagram, so you can trust angles. So 45 degrees is a null direction. So this is a null direction. What is this null direction? Is where all the massless ray or particles or whatever end up being. Okay. So if you have, let's say, two black holes colliding here and producing gravitational waves, all these gravitational waves will travel and end up in this line, okay, in the null infinity line. And this is the parametrization of what we know as asymptotically flat spacetime. Asymptotically flat in this sense is being close to Minkowski spacetime, but close to this line. Okay, this is the notion of asymptotically flat spacetime. And then you make the question, what is the kind of symmetries that preserve this set of metrics, namely the set of metrics that are asymptotically flat, very far, close to null infinity, into itself? Not necessarily metric to itself. This is not an isometry. It's an asymptotic isometry. It's one member of this set to the same or another member of the same set. Of course, the restriction is weaker because you are not asking a metric to be itself after the diffeomorphism. You ask a member of a set to be another member of the same set. The restriction is weaker, the answer is stronger. And actually, if you make computation, you compute the symmetries, asymptotic symmetries, lead derivative, then you get some infinite number of Killing vectors. So we know that strictly Minkowski space is, of course, invariant under time translation, just in the real time. So this is time translation, conservation of energy. But if you ask the asymptotic isometries of Minkowski space, you will realize you don't only have rigidation time, but also multiplied by an arbitrary function of zeta and zeta bar are the angular coordinates, those that are not here in the diagram. So theta and phi, if you want. So we have infinite amount of translation. This is called super translation. It's not supersymmetry, just a bad name for it. Because you have a translation, but in time, but for each point of the celestial sphere, you make a different translation in time. Okay, this is why the set is infinite dimensional, because you have one transformation for each function, and the function is arbitrary. And then this has been reconsidered, especially after knowing about this kind of notion of asymptotic isometries related to holography. We learned this from the 90s with ADST. So it was this idea whether it was possible or not to use this idea to make a holography kind of picture in asymptotically flat spacetimes. Okay, and apart from the papers by Glenn Barnish, Cedric Rossert, and all these friends from Brussels, who initiated this new reconsideration of this VMR symmetry, there is an amazing line of research by Andy Strominger and his group, such as Ivyudev and all these people, about how to understand this in a modern perspective and make connection between soft theorems, word identities for Weinberg theorems, asymptotic symmetry, memory effects. I will not talk about that, and because it's not strictly connected to my talk, because my talk will be a little bit different. I will not look at the thing close to null infinity, but close to the horizon. This is the Penrose diagram from a black hole. So this is the horizon, this is flat infinity. So the question is whether the same story that happens here happens close to the horizon. And the reason why to look at it is you can motivate, of course, you know, once you find something, you can have a mito de origen and reconsider the story and play that out, of course, because I'm very intuitive. No, I mean, a little bit by chance, a little bit playing around, a little bit with similarities, we realized that something like that could happen. Now, a posteriori, it's easy to understand why, but at that time we were confused. But then it appeared a paper by Hawking, which is actually not a paper, it has a transcript of a conference saying that he was expecting to, in 2015, also to have infinite dimensional symmetry close to the horizon. So this motivated us to look for it, and actually we found it. So I want to describe how we found it. So again, the idea is to mimic what the people did here, mutatis mutandis, close to the horizon. We will see that it's not exactly the same, the algebra is a little bit different, but the idea is similar. Look for the asymptotic symmetries that preserve the form of the metric close to the horizon, okay, in a very specific sense. So this is a specific sense. So we consider this metric, which is, there is a theorem you can play. It's actually not a dynamical theorem, it's a kinematical theorem. So this is geometry. This is valid for any theory, not necessarily a solution of Einstein gravity. And then you can find that if you are close to a non-singular horizon, doesn't matter if this is extremal or non-extremal horizon, even if it is not an isolated horizon, it also works. It can work for event horizons, Cauchy horizons, apparent horizons, cosmological horizons, black hole horizons, or whatever you want, acceleration horizons. You can always find the metric in this form. There is always a system of coordinates. You can put the metric in this form. Let me be a little bit more precise. So this is the null time on the horizon. You know that your time coordinate, as long as you approach the horizon, becomes a null direction. So this is the time on the horizon, which becomes null. So rho is, rho measures the distance from the horizon. Rho equals 0 is the horizon, and this measures the distance from the horizon. And then you have this function here, this function that depends on your solution, but there is always a way of writing like that, with this falling off. So then you can always ask yourself, which is the symmetries that preserve this form of the metric, and probably changes after a transformation to a different n and a different omega, but leaving the same fall off. Okay, that's the reason. So then you ask this question, and then you find this solution. Namely, these are the Killing vectors that make this show for you. You take one of this metric, you apply this, and you get another metric with different n, different omega, but with the same fall off. Asymptotically, it's the same behavior. And actually, these Killing vectors are parameterized by a set of of arbitrary functions. That's why they are infinite. Whichever function t of the coordinates, angular coordinate you put there, any function L 1 or 2, because A goes from 1 or 2, is actually a good symmetry. And this is the transformation you generate. Again, you preserve the asymptotic, but changing the functions. And then you can make subsequent analysis of this and apply it to and make the commutator, and you find the algebra. It's the generalization of the isometry algebra. It's asymptotically isometry algebra, which is infinite dimensional. This is valid so far for any horizon. Now let's consider the extremal ones. In the extremal ones, t, this function that is arbitrary, factorizes in two. One that is independent on time and one that is linear on time. And then you can see the algebra. This is written in a fancy way, but this is nothing but saying in a fancy way 2 copies of Virasoro algebra coming from these pieces. You can see it, roughly speaking, from here, the fact that 2L gives an L or something like that. And it's in semi-direct sum with 2 infinite dimensional currents. Are so-called super translation currents, the one that we find also at null infinity. This algebra is a little bit different from BMS because it's the structure constants are a little bit different, but contains as a subalgebra also Virasoro, also super translation infinite dimensional. And then as a symmetry, you can get many other charges associated to them, and you have to compute them. You need some robust method to do that, so we use here in particular the Barnich-Brand formalism, but you can do it with different methods, and then you can find that actually these charges are non-trivial. So which means that these transformations are not pure gauge, because it could be that there are an algebra that doesn't produce nothing new. It actually turns on charges when you make this transformation. And inside this big set of similar to BMS symmetries we found BMS itself. So BMS is a particular case of our infinite dimensional algebra, the one that we find in the horizon. So we can say then that indeed there are some BMS kind of a structure inside of the horizon. So as this conjecture by Hawking of 2015, now we can make it precise. Indeed, we found that inside and close to the horizon of any black hole, especially in the case of extremal black hole, we have infinite dimensional symmetries, and that deals non-trivial charges. And if you ask yourself, well, which is the physical meaning of these charges, well, you evaluate unknown solutions for which you have some intuition. And you can see that one of the charges, for instance, is the Wald entropy. So this is an infinite dimensional generalization of Wald-Nether charge. And also you can find the angular momentum, but now computed from the horizon, not from ADM kind of infinity. And this is very interesting because it allows you to consider, for instance, charges of black holes that are not asymptotically flat. For instance, accelerated black holes or magnetized black holes. So for this, you can see the talk by Sasha, a couple of talks later. So thank you very much.
Okay, thanks, Gaston. Are there any questions or comments? Sumit, please go ahead.
Hi, my question is this, like, can we do the same thing for, let's say, a Cauchy horizon? And is it necessary to have a black hole horizon?
No, it's not necessary. Actually, for instance, we consider this for apparent horizons such as acceleration horizons, like Rindler spacetime, for instance. In that case, you can compute the charge. The charge will be infinity, but that's trivial because the entropy is infinity. But you can compute the charge per unit of area, for instance. And this is finite, and it's what Laflamme computed in 1992, the entropy per area of a horizon, and you get exactly the same result. So the answer to your question is yes, you can do it for not necessarily event horizon, but cosmological horizon, apparent horizon, such as Rindler spacetime.
Okay, so
the answer was yes. I'm sorry, I'm kind of talking too much.
Oh no, yeah, thanks.
Yes, just a naive question. Is it hair? Did you have more hair, or is it some kind of charge that can be?
Yes, this is a very good question. Yes, this is what the people call soft hair, and the reason why it's called soft hair is because the new charge you turn on commutes with the energy, so it doesn't change the energy. If you have a zero energy configuration, you will produce a different zero energy configuration. Just kind of saying that your vacuum is degenerated. That's the reason why the people, Andy Strominger and these people, use the soft hair. But indeed, you are turning on hairs on this black hole. And the reason originally it was meant to try to be understood to contribute to the solution of black hole entropy paradox, the information paradox, but I don't think it has application for that. That's why I don't talk about that. But yes, the answer is
okay,
yes.
You think that there is not enough hair then to count those states at the quantum level?
Yeah, exactly. So we do have a measurement of entropy at classical level because one of our charges is Wald entropy, but this is not enough hair. That's a good point to do. It's not hairy enough to quantum mechanically reproduce a kind of Cardi formula computation.
Okay, thank you.
So
at least in our approach.
A question from Joaquim, and also in the chat box, then there was a curiosity by Lucas Maldone.
Okay, you understand my question?
Hi, Kim. Nice to see you.
Oh, same. You were saying historically BMS symmetry has appeared as asymptotic symmetry on flat space-time, or as you have shown for the near horizon geometries of black holes or something like that. But very recently has been a paper by Bring that they have found this BMS symmetry as a short radical symmetry in the light cone gauge without any reference to asymptotics. And also, I should say that there was an old study by Longhi and Materassi where they were finding BMS symmetry studying the Klein-Gordon field. Therefore, I don't know how much BMS symmetry is really related to asymptotic symmetry.
Yes.
And okay,
I fully agree. And it's actually more related to, and this, our work goes in the same spirit, because it's more related to the fact that you are playing some game on null surfaces, and then imposing some boundary conditions or special data on null surfaces. It doesn't matter if this is an asymptotic region or a horizon here. Or even as the question of the fellow before, it can be also a render horizon, like accelerated horizon that is anywhere in our space, but is a horizon of someone, but is here in the middle, you know, in Valparaiso or something. So it's more related to the null, to the fact that you are playing some boundary conditions on null surfaces. But I don't fully agree to make a big picture out of it, so I would be pretentious if I try to give you an answer like that, but the feeling I have, but yes. I think it goes in the spirit of this paper.
Okay, thank you.
Thank you. So maybe we have time for Lucas' question.
Maybe you already answered because my curiosity, in fact, was about this. Sorry, the fact that you find BMS. I was thinking to the particular case of sparse-shaped black hole and near the horizon. You know, you are essentially Rindler times two-dimensional sphere, so you are essentially flat there. And so I want to understand if this fact that you find BMS was related to the fact that near the horizon, in that case, for example, you are flat. And that was, but you say it's more related to the presence of null surface.
Yes, let me make two comments about that. First of all, is that this is a way I would motivate it like that. Close to a horizon of any static black hole, which is non-extremal, you will find flat space, roughly speaking. As you say, it's Rindler croissant. And then it's not weird to find something that you find in asymptotically flat. However, let me make two comments about that, two cautionary notes. First of all, the algebra is similar to MS, the one you get in the horizon, but not exactly the same. You can see that the structure constant are a little bit different, okay? A little bit larger, because the boundary condition you pose there are a little bit different, and that's the reason. It's the same space, but with different boundary conditions on them. Second, notice that here, I also find that that's the reason why I remark this point in extremal black holes. And in extremal black hole, you don't have Rindler space, you have 82 cross something, and still you find this symmetry.